Okay, hi. You can scan the QR code if you want to click on the links in the slides, otherwise it's not very useful. So my name is Matt Bovel. I'm a PhD student at EPFL, and I work between two labs. I work with Martin Odersky on the Scala compiler, and I work with Viktor Kunchak, who is making the stainless verifier that allows you to prove some properties on your Scala program. And basically, my job is to make a link between these two labs, and in particular to bring some of the verification features of stainless into the Scala compiler. So what I present today has been also done in collaboration with two students, Quentin Bernet and Valentin Schneeberger. So let me show you a motivational example first, so that you understand why I want to introduce these logically qualified types in Scala. So here you see a zip function. So the zip function takes two lists and creates a list of pairs where the first elements come from the first list and the second elements from the second list. So as you know, in the Scala standard library, if the two lists don't have the same size, the result is truncated to the shortest list. However, you might have made a mistake if you don't pass two lists that have the same size. So maybe you want to verify that. So how could you do it today? Well, you could use assertions. You could add a require, so that's basically an assert, but that checks a precondition of the function. You could require that the list of both sizes are the same, and at the end you could add the ensure, that's also just an assert for a postcondition, to document that the result has the same size as the inputs, okay? So that's nice. However, it comes with some limitations. First, that's a runtime check. So you pay for some overhead at runtime. Also, you have no static guarantee. So it's only checked for the inputs that you will actually pass to the function. You don't have any guarantee that that works for all inputs. So same problem as for unit tests, right? You just check some specific instances of your problem. It's not part of the API. As you can see, it's inside the function, so you don't see it in the documentation. And we will come back to that later, but it's a bit hard to compose. So we have a lot of support for types in Scala. You can pass type parameters around, for example. With assertions, you cannot make use of these features. Okay, so another possibility could be to use existing advanced Scala types. I will not spend too much time on that slide because I don't have time to introduce all these slides, but basically if you use path-dependent types, compile time operation, match types from Scala, you will also have some limitation that works only to describe the fields of object. For example, it's limited to basic reasoning like constant folding and reasoning about constant, but you cannot encode much. Another problem is inference. These very advanced Scala types are hard to infer. And last but not the least, you have a completely different language now to talk about your assertions if you encode them at the type level. While with the nice assertions we had before, it's just terms, right? You just write that code like you would write any Scala code. So what could we do? Well, my proposition would be to introduce what we call logically qualified types. These types basically allow you to lift assertions at the type level. So here is again the signature of the zip function, this time with logically qualified types. You see that we require a list of B, and after you have this with, and then you have a condition. This condition is just a term, an expression that is of type Boolean, and that must be true when we call the function. Similarly, you see here the return type, that the result that we name L here has the same size as the input. Okay? So I wrote that here. The return type means that any value L of type list AB here, such that the condition is true. So we define effectively subset of values of some type that fulfill a condition. So that's absolutely not new. It exists in many other languages. It dates from the 90s. The most known implementation is liquid types for Haskell. And we also had some previous work in Scala. So I will not have time also to go through all these different existing implementation, but maybe just one main difference with liquid Haskell that we have is that we want to treat these qualified types as first-class types. In liquid Haskell, it's a bit different. Actually, liquid Haskell is a plugin. It doesn't work in the main liquid Haskell compiler. And you write these refinement types as comments. So you see them in green here, okay? So you have like 2 layers of types, which is exactly what I would like to avoid in Scala. I would like to have a simple system where these types integrate and are written exactly like other Scala types. Okay, so let's just see the syntax a little bit in details because it might seem strange at first. But you see a qualified type starts with curly braces, then you have the binder, which means for any value of that type. Here you have the parent type, and then you have the condition. Just to note that it should not be confused with the existing structural refinement types that we have in Scala and that we saw this morning, for example. So structural refinement types are a bit different. That's an existing feature in Scala that allows you to refine the type of a field. But these types, they also start with curly braces, but then you see a val or a def afterwards, while the logically qualified types start with a binder, then a parent type, and then an assertion. We also have a shorthand syntax. So if we have this example of zip here, with the full syntax, the long form syntax, you would need to repeat the BS binder here inside the curly braces. However, we already have a binder, we already have a name for BS, so you can just omit it, omit the curly braces and the binder all together and just write the qualified type like that. So you can reuse the BS binder that already exists. Okay, so that was an example for zip. We could also define the type of concat that concatenates 2 lists together, for example. Here the result has the size of the sum of the size of the arguments. And what you can check today with my prototype, for example, is that if you concatenate 2 lists, x's and y's, and you also concatenate 2 lists, y's and x's, and you zip them, then that type checks because the system can derive that they have the same length because the length of x's plus the length of xy's is the same as the length of xy's plus the size of x's. If instead you try to concatenate 2 x's here, you will have a list of a different size than the first argument, and then you will get a compile time error. Okay, so just a note on what can you write as predicates, so what can appear there. We talked before a lot about functional programming, about properties of functional programs, and in particular, we want to work only with pure and immutable functions and data structures. So if, for example, you refer a var in your predicate, you might be in trouble later because, of course, x might change. So the fact that y has that type corresponds to this predicate is only true as long as x does not change. And that would be very hard to track, so for now we just forbid it. You cannot refer to mutable variables from a predicate. Something else may be a bit less obvious that must be forbidden for soundness is equality on classes that are not case classes, because as you know in Scala, normal classes have reference equality. So actually here you create 2 different instances of the box class, here on the right-hand side and here in the predicate, and these 2 would not be equal from the equal method, right? So that we also forbid. So if I have to summarize it, currently the predicate language is restricted to fragment of Scala consisting of constant, stable identifiers, field selection over val fields only, pure term application, type application, and constructor of case classes without initializer. And where you don't override the equal method, of course. Currently, we are actually not checking that functions are pure. That would be an extension of the system. And we are also not sure that would be a good idea in general, because it would require a lot more effort from the developer to prove that all their functions are indeed pure. But that might be future work. Now you might ask, okay, nice, we have these types, but how do we actually get an expression of that type? Because as you know in Scala, the type, for example, of x plus 1 is just an int. And we don't want to change that. We don't want from one day to the other to say now, every time you use plus in your Scala program, it will get a very precise type that is a qualified type. No. For backward compatibility, it's absolutely not an option. Also for performance, it's not an option. We don't want these big types everywhere. Instead, we want to introduce them only when they are expected, because we always know what the expected type is in Scala. So if you do write an explicit type annotation, like here, then the system is able to derive that indeed you have an int that is not only an int, but that is equal to x plus 1. This simple process has a name, it's called selfification, but that essentially just means that if you have an expression E, you can give it the qualified type x equal E, okay? We can also do that if you have function in your expression. That's something that would not have been possible with the existing things in Scala, for example. Sometimes you still don't know exactly what the value is. Let's say I'm reading something from user input, for example. There is no way I can give it a precise type directly. So what can I do? I can do a runtime check. How do we do runtime check in Scala? Well, we have pattern matching. So let's say I'm reading an ID and I want to make sure that it matches a specific regular expression. So here it's a regular expression that defines what the valid ID is. Well, I can just define a type alias ID here. So it's all strings that match this regex. And then I'm able to match on that type, and that will effectively insert a runtime check, checking that my value matches this regex. And when I'm in that branch, ID has the type ID, so I'm sure it matches ID regex, okay? Sometimes we want to just fail if the test does not work, so you have a shorthand for that. It's called .runtime checked. You can write it like that. And that just desugars to a check where we cast if the predicate is indeed true, and otherwise we throw an illegal argument exception. Okay, and of course, as with any other Scala type, you can also do just full unsafe checked with as instance of, and these are not checked at all, but that would not be the goal to use that, of course. Just a note, as you know in Scala, type parameters are erased, so we don't have access to them at runtime. So in the case of a list, for example, you cannot match a list of something, whereas it's a qualified type or not, that in general in Scala. What you can do, however, quite easily is to use the collect method, for example, and that would convert my list of int to an list. So basically it filters the element, and then it ensures that the resulting elements indeed have the type pos, right? So it filters and map at the same time, if you want. We could also define a shorthand for that, but I don't know if that would be useful. Okay, just then a note, well, more than a note, but a few explanation about how subtyping works for these qualified types. How do I know that a qualified type is a subtype of another? Well, there are two things to check. First, if I have this qualified type here where the parent type is T, and this one where the parent type is S, I need to check that the parent types are subtype of each others. And then what do I need to do for the predicates that are attached to each of these type? Well, I need to check that for any value, if the predicate of the first qualified type is true, then the predicate of the second qualified type is also true. So we need a solver that is able to check logical implications. And that's exactly what SMT solvers that we saw in the previous talk do. in this prototype, we're not using an SMT solver. We just implemented a simpler, more lightweight solver that is based on a few things that I will describe quickly, but basically constant folding, normalization, unfolding, and equality reasoning. So constant folding, I think it should be pretty clear what it does. It will reduce operations on constants so that you know that 1 plus 1 is equivalent to 2, for example. Normalization enables you to reason about algebraic properties of operations, for example, on integers, so that you know x plus 1 is the same as 1 plus x. That's what we needed for the example zipping to list, for example, where the size were both symbolic, but we needed to reason about commutativity of addition. And we have other normalizations as well. We have something else, unfolding of local value definitions. And I think that's very important. I said before that it's hard to do inference well for that kind of advanced types. And we don't want to type everything with very precise types. So that enables you to have here a y that is just an int. It doesn't have a precise type. But if you use it in a subtype check, the solver will be actually able to see the definition because it's a local val and to unfold it. So it will derive that y and x plus 1 are actually the same thing. And I think this is crucial so that you don't need to write these explicit types everywhere, but instead they can be recovered from the definitions. We also have some kind of equality reasoning. So if something is equal to something and that thing is equal to something else, we know that the first and the last things are equal by transitivity of equality. We also have congruence of equality. That's some properties that we can check. We use an egraph-like data structure to check that. Okay, so that's what the solver can do today. We also have some compatibility with other Scala types. So we have literal types in Scala. That's actually a type. And we can know that if we have a qualified type saying the value is equal to 3, that's actually the same. And we plan to support interaction with other Scala types in the future. Okay, so what is the future work? Well, it's to fix some bugs, of course. Then we want to make a pre-SIP. So a SIP is a Scala improvement proposal document to actually get the feature into Scala. So we will first do a pre-SIP to get feedback from the community and then hopefully make a SIP and standardize the feature. Okay, so I will not talk about the future work unless there are questions about that. I will skip to the conclusion slide. So I presented the syntax, how we can introduce these qualified types with selfification or runtime checks. I showed you a bit what subtyping we support today, and I told you about the future work that is the SIP. Okay, thank you very much, and if you have any questions.
Thank you, Mathieu, for your presentation. Any questions?
Thank you so much for the talk. We've been working on Liquid Java for a couple of years, so I'm really curious about some of your decisions and how could they integrate with our work so you could support at least some mutable stuff in your project. But I think right now you don't support uninterpreted functions or measures, as they're called in Liquid or logical qualifier.
No measures, but uninterpreted function, yes. If you just call a function, it will be considered as an uninterpreted.
So how do you do the pattern matching there? Because you cannot runtime assert it, so.
So I think we can already do some things with pattern matching, but as soon as you have recursions, so we would need measures there, and indeed there will be some more work to be done. Yeah.
Okay. And I would be curious to talk to you about the later stuff that you skipped.
Yeah.
Thanks. Any other question? Okay, so let's thank Mathieu again.